Welcome to Chapter 2, Measurements and Calculations. This chapter gives us the mathematical and measurement tools that we will use throughout the rest of the course. We will work with the scientific notations, units, metric prefixes, significant figures, dimensional analysis, temperature conversions, and density. Yes, there were a couple things there. None of those ideas stand alone. They are all the language we use to report measurements and problem-solving tools we use to move from one quantity to another. As you work through this chapter, pay attention not only to getting a numerical answer, but also the units and the number of meaningful digits in that answer. Quantitative observation. A measurement is a quantitative observation, meaning that it includes both a number and a unit. The number tells us how much of a thing we have compared to a standard, and the unit tells us what scale we are using. A value such as 25 is by itself incomplete, in chemistry at least. 25 grams, 25 milliliters, and 25 degrees are very different statements. Throughout this course, get in the habit of treating a unit as part of the number rather than something added at the end. Measurement continued. Scientific notation is a way to express very large or very small numbers in a compact form. We write the numbers as a value between 1 and 10 multiplied by the power of 10. The example on this slide takes a large ordinary number and rewrites it so there is a non-zero digit to the left of the decimal. Scientific notation is especially useful in chemistry because we routinely work with quantities that range from the size of atoms, remember Avogadro's number, to the number of particles in a mole. When converting a number into scientific notation, the decimal point tells us the coefficient and the number of places it moves tells us the exponent. We move the decimal unit until the first part of the number is between 1 and 10. Then we count how many places it moved. The direction of the move determines whether the exponent is a positive or negative. Those two decisions separate. First, determine the direction the decimal moves. Oh, I gotta redo that. No, Here are the two common cases. If the decimal moves to the left, as in 345 becoming 3.45 times 10 to the second, the exponent is positive. If the decimal moves to the right, as in 0.0671 becoming 6.71 times 10 to the negative second, the exponent is negative. A useful reasonableness check is to ask whether the original number was larger or smaller than 1. Large numbers generally need positive powers of 10, while numbers between 0 and 1 generally need negative powers. So your hint when you're looking at any of these is, was my number smaller than 1? Then I need to make sure my exponent is negative. If it was larger than 1, the exponent should be positive. All right, our concept check here, we have to put 7,882 into scientific notation. So let's start by figuring out our decimal point. It's right there. Don't forget, if we're moving this direction, we are moving positive exponents. If we are moving this way with our decimal point, that's negative exponents. We're going to move 1, 2, 3 to get a number between 1 and 10. So it'd be 7.882 times 10 to the third. Let's look at our options. No, no, yes, and no. That one snuck one by. I tried to put a negative. We know it is C. That's also a negative, remember, and this number was larger than 1, so it can't be negative. All right, on this one, we are moving the decimal to the right, and also this number is way smaller than 1, so we know we're working with the negative exponent. We're going to move our decimal 1, 2, 3, 4, 5 times. That'd be 4.96. And we moved 1, 2, 3, 4, 5 times 10 to the fifth. But it's negative because we moved to the right. Ooh, and that looks like 5 is our answer. Remember, had to be negative, so this one went away right off the bat. All of those are in correct form. We just didn't move that far. Now, let's go one step further. The unit is a standard or a scale used to report a measurement. Scientists need common units so that measurements can be understood and compared anywhere. You may be familiar with our very good, nice American system, but science works most generally with the metric system and more specifically the International System of Units, or SI. SI provides a internationally agreed upon set of base units that we use and their derived units, meaning units that have multiple different units inside them, like density. In this course, units are not optional. They are part of the information in a measurement and part of the logic we use in calculations. Here are the common SI units that we will be using in this class. Mass, we are going to measure in kilograms, length in meters, time in seconds, temperature in Kelvin. Remember, there's no degrees, just capital K. Electric current is in amps, which is capital A, and the amount of substance is a mole. Remember, those are all very important. Make sure you are aware of the capitalization, and if there is a degree sign, you'll notice none of them have a degree sign. The other thing we need to know how to do is use our metric conversions, which is by putting the metric prefix in front of a unit that allows us to change it without changing the quantity being measured. That table that you see right now shows common prefixes along with their symbols and the power of 10. So for example, kilo means 1,000 times the base unit, centi means 1/100th, and milli means 1,000th. Rather than memorizing that whole table, because we don't need to, other than King Henry died by drinking chocolate milk, you just need to know the prefix and what the scientific notation power is. Those powers of tens will become the conversion factors later in this chapter. The SI unit of length is a meter. So this table shows you different ways that we can use those metric prefixes to make a larger or smaller meter. A kilometer is 1,000 meters. A centimeter is 1/100th of a meter. And a millimeter is 1,000th of a meter. The important point, hopefully, that you're starting to see here is the relationships are powers of 10. That's why we can just move the decimal, but also it makes changing it in scientific notation much easier and sets our dimensional analysis methods very easily. Volume, something you should all be aware of, are the common measurements of volume. You'll see down at the bottom that volume is measured in cubic centimeters, but if we have a liquid, we're going to want to measure that in milliliters. Turns out a milliliter is equal to a centimeter cubed. And later on, if we're working with something bigger, a liter is equal to a decimeter cubed. We will need to know those relationships when we work in density. Mass. Mass is a measure of the amount of matter in an object. Remember that mass and weight are not the same. We will be using kilograms in the SI units. A lot of formulas use it at least. In the lab, we're almost never measuring something that weighs more than a couple grams, so we'll need to know how to convert quickly between them. You do not need to know how to convert between a pound and a gram or a kilogram and a pound, but generally you should be aware that a kilogram is about 2 pounds and a pound is about 450 grams. We'll use the internet for those calculations. Concept check 3. Which of these statements is using the wrong units? A gallon of milk is equal to about 4 liters of milk. Sounds about real to me. A 200-pound man has a mass of about 90 kilograms. Well, we just said there was about 2.2 kilogram, 1 kilogram to 2.2 pounds, so that sounds about right. A basketball is 7 meters tall. Let's draw a sketch. All right, so we'll draw me. Right, I'm right at 2 meters. Okay, that's me. I want to play basketball, and of course, let's see, 2, 4, 6. About we got my basketball. And that's right. Oh, that's not right. So that one's wrong. We know that. And a nickel is 6.5 centimeters thick. Let's see. I've got my hand here, right? I got my hand. I have a couple coins. If I look at them between my fingers, of course, that's how big the edge of a dime is, right? It's that thick between my fingers. No, that's also incorrect. That is, in fact, nowhere close. I bet if we had to check, a nickel is probably about 6.5 millimeters thick. But you just need to know your important habits are to make sure your units make sense. And we're right. Every measured value has some amount of uncertainty. With a measuring device, some digits can be read directly from the scale, and then one final digit is estimated. That estimated digit is called the uncertain digit. We record all of the certain digits first, and then one uncertain digit. The idea is the foundation for significant figures. Significant figures are not an arbitrary set of math rules, they are a way of communicating how much precision the measurement device actually supports. In this great example here with the ruler, you can see why we have uncertainty. The actual measurement on the ruler reads to the tenth of a centimeter, right? So right here, we can see the 5 perfectly, right? But on a ruler like this, we cannot see the 5. It is not measuring that place. The pin is about 2.85 centimeters long. We can guaranteed read the 2.8 part because the marks in between are directly measuring the 8, but we cannot say for certain the mark in between, which is why they drew this in here, and why I'm kind of crossing it out, because it doesn't have that. This is the mark that ruler has, and this is the mark. We can see it lands in between those marks, so that's why we add that uncertain digit. Different measuring tools have different measurements that they have in their level of precision. Now we need to talk about the rules for counting significant figures. Remember that all non-zero digits are significant. So a number like 3,456 has 4 significant figures. Zeros are much harder to figure out. Leading zeros, which appear before the first non-zero digit, are placeholders and are not significant. So 0.048 has 2 significant figures. Captive zeros, which fall between 2 non-zero digits, are always significant. So 16.07, captive between the 6 and 7, 6, 7, has 4 significant figures. The location of a zero, not just the fact that it is a zero, determines whether or not it counts for its significance. Trailing zeros are zeros at the right end of a number. On this slide, they're significant when a decimal point is shown. So 9.300 has 4 significant figures. A number written as 150 without the decimal point is treated as having 2 significant figures. The exact numbers are different. Values obtained by counting or defined equalities like 1 inch equals 2.54 centimeters are considered to have unlimited significant figures, and they do not limit the precision of your calculations. So if I have 9 pencils, I counted those, there can't be 9.1. And if I'm converting something, I use the full conversion factor. I can't say, oh, well, 1 inch is actually equal to 3 centimeters, because then everything would be off. If we look at scientific notation, we'll find that it's very useful for showing significant figures clearly. If we want to write 300 in significant figures properly, all we have to do is put it into scientific notation. So we would write 3.00 times 10 to the second. That coefficient, 3.00, tells us immediately that the value has 3 significant figures. This avoids the ambiguity that can occur with trailing zeros in ordinary notation. Scientific notation also makes very large and very small numbers easier to read, so that reduces the chance of losing track of a zero during a calculation. Rule number 1. When we round a number, you first look at the digit that will be removed. If it's less than 5, the preceding digit stays the same. If it is 5 or greater, the preceding digit increases by 1. So the example 5.64 rounded to 5.6 and 5.68 rounded to 5.7 when the 2 significant figures are required. The same rule gives 3.861 rounded up to 3.9 to two significant figures. Always decide the required precision before you round. You're usually better off not rounding until the very end. In a multi-step calculation, do not round in every single step. Carry all of your extra digits on your calculator or program through the calculations and round only the final value. Rounding too early can introduce avoidable error, especially when several steps are involved. You can keep intermediate values in your calculator. They're known as guard digits if needed, but the final reported value should reflect the correct significant figures or decimal places for that problem. For multiplication and division, the answer is limited by the measurement with the fewest significant figures. For this example, 1.342 has 4 significant figures and 5.5 has 2. The calculator, when we do that, gives us 7.381, but the final answer must have 2 significant figures because of our 5.5, so we must report 7.4. The rule is based on significant figures, not decimal places, when we are multiplying or dividing, and a lot of the time we are multiplying or dividing. For addition and subtraction, completely different rule. Here, the limiting measurement is the one with the fewest decimal places. Okay, so not the fewest significant figures, but the fewest decimal places. The values on the slide line up by decimal place, like you should. And the final answer is rounded to the least precise place value among those terms. Do not use the multiplication and division rules for addition and subtraction. A helpful strategy is to line the numbers up by decimal point and identify the last place that all the measurements are supported. So you see on this one, we have 2 decimal places here, 3 here. Our final value can only have 2 because that third one is an unknown. We don't know if that could be measured here. We would be uncertain if we were using that measurement, like our pin. That would be a mark beyond whatever measuring device that was. So we can't use it. We can subtract our numbers and then round. But right now, we just want a number. A helpful strategy, again, line them up, and then you can see which is the last supported decimal place, meaning which one is in all the numbers you're working with. Concept check 4. You have 2 graduated cylinders. One cylinder can read to the 10th place, and one reads to the 100th place. We will add them, and the first cylinder limits the precision on the second one, right? Or does it? Let's check. We have water in each of these graduated cylinders, right? And on this one, looks like we have graduates every let's say 20%. So we know this is 2.2, 2.4, 2.6, 2.8. So the meniscus hits at 2.8. So we can 2.8. And we can measure that because we have the graduate, which means we could put in an estimated digit, right? And I'm going to say it's 1 because that's for me. And those are milliliters, but I can't write that with my mouse. Okay, and then on this side, we have graduates, also every roughly 20%, but we are going in the 100th place. So we have 0.3. Nope, sorry. I can't go back. Oop. 2. We're going to give this one an 8, right? Because it's in the same spot. And let's throw in our estimated digit there. If we add those together, we would get 3.1 and some other digits. And since we're adding, the 1 that we're putting together just comes from us only having that second digit. So let's see what we would get. Beautiful. Which limits the precision? Well, this one, right? Only has 2 decimal places, and this one had 3 decimal places. Ignore that. Remember, on our adding and subtracting rules, it's whoever has the least amount of digits, decimals specifically. What is dimensional analysis? You might be wondering. Dimensional analysis is the main conversion method we use when we are converting one thing to another. Starting with the quantity you are given and then multiplying by one or multiple conversion factors, like when we use moles. Each conversion factor comes from an equality set between two units. We don't have to determine those, they're given to us. Arrange the factor so the unwanted unit cancels out and the desired unit remains. Then we complete the actual arithmetic part, apply the correct significant figures, and ask whether the answer is reasonable. That's a pretty important step. Treat units like they are algebraic quantities, and that'll help us set up the equation properly before we calculate, meaning that we should put them like our moles to gram calculation and cross things out as we go. And then ask ourselves, does the answer make sense? Here's our first example. If we were to convert 6.8 feet into inches, we know that we need an equivalency factor between feet and inches. We know, because we're Americans, that 1 foot equals 12 American inches. So I would put my conversion factor against my known value, and we will get, let's see, I don't actually think it gives us the answer on that. I'm doing it right now, guys. Live and in person, I'm going to take 6.8. I'm going to multiply it by 12. You get 81.6 inches. I wonder if that's on the next slide. I don't remember. But our goal is not to memorize which way to place our factoring, but let the units tell us. Oh, it keeps going. Whew. Now we can check my work. All right. Because our starting unit is feet, we want inches. The feet must appear in the denominator because we want to cancel those out like in algebra. Therefore, we multiply 6.8 feet by 12 inches over 1 foot. That's the conversion factor. The feet cancel out, leaving only inches and our actual numerical value. If the units don't cancel the way we expect, stop doing your math and fix your setup. Unit cancellation is one of the best built-in error checking methods for all the chemistry calculations. Alrighty. So if we finish our conversion, let's look at what it gave us. 6.8 feet times 12 inches over 1 foot equals 28 inches. Let's do our last step. Does the answer make sense before we even go to significant figures? I don't know about you guys, but I know 1 foot is 12 inches, and 2 feet is 24 inches, and 4 inches further than that certainly doesn't equal 4.8 feet. So we must need to go back and check our conversion factor. I believe the example they're trying to show us is that if you do the conversion factor wrong, you won't get the right answer. However, our significant figures should be 2 because we are doing a conversion factor, which would give us, instead of 81.6, 82 inches. And now we'll do this example where we're going to have multiple steps to get to where we need to go. If we have an iron mass sample of 4.5 pounds, what is the mass of the sample in grams? We're going to need to set it up like this. We start with pounds because we know we're in pounds, which means we need the conversion factor for kilograms to pounds with the unit we want, or at least the step we need to take, on top. Then we have the unit that we don't want on the bottom of the next piece, which would be right here, and the conversion that we do want because we want the answer in grams. Bing, bam, boom. There we are. 2.04. Because it's a multi-step dimensional analysis problem, we needed to arrange our factors that cancel pounds to make kilograms and then kilograms to make grams. That same method works whether there's one conversion factor or a bunch. Keep building the chain until you only get the unit you want out on the end. All right, so here we are. The concept check that'll actually put your knowledge here to the test and maybe make you feel like you're in math class. This is not about plugging into and memorizing a formula, about a solution. To estimate the cost from driving to New York to Los Angeles, we need a distance, a fuel efficiency in miles per gallon, and a price per gallon. Using the sample estimates, we can convert miles to gallons, and then we can do gallons to dollars. So let's make sure we've all read the problem, and then we will try to set this up. We should start with our miles because we're trying to figure out how much money we're going to spend, and we have a distance. 2,500 miles. Next, we need to know what our efficiency is. And nice for them, they did 25 per gallon. Remember, that's per 1 gallon. So that'd be 1 gallon over 25. And that would be miles. So if we were checking these two against each other, 2,500 times 1 gallon over 25 miles would give us a number in gallons, which we could then use against the average cost of gasoline. Don't we wish it was back to 325? Anyway, we would put 1 gallon on the bottom of the next one, like so, over, and then our numerical value because we want to know how much money it takes. And I believe that is on this slide. If we check, boom, and then I don't have to do the math. However, if you were paying attention, this is a pretty good model, right? You should be able to somewhat estimate. We'd be in the 300 range based on the cost, the amount of miles, because 2,500 is divisible by 25 100 times. 100 times 3.25 is 325. I wish it was that cheap. $325 in gas would be great to go from LA to New York. All right, here our temperature units are on the slide. You should know these three scales and remember that we mainly work in one of them, and it's Kelvin. Fahrenheit is our familiar one we use in the US, Celsius, the rest of the modern world, and Kelvin is our absolute temperature scale. It's also used in conjunction with Celsius, as you'll remember. But be careful on the symbol with Kelvin. Remember, it's just capital K. There's no degree sign because it's an absolute scale. Temperature conversions require equations because these scales have different 0 points. For Fahrenheit and Celsius, there are different interval sizes between the degrees. 1 degree increase for Fahrenheit is not a 1 degree increase in Celsius. A 1 degree increase in Celsius is 1 temperature change in Kelvin, though. This nice diagram right here explains that point beautifully. The three major temperature scales are up here, Fahrenheit, Celsius, and Kelvin. You'll notice that when one goes down in Celsius or Kelvin, the other one goes down 1 as well. That is not true over on Fahrenheit, since it is using a completely different scale for its degrees. Kelvin begins at absolute 0. Remember, that is the point where all particles cease to move. And it does not have the capacity to use negative values in the ordinary range, at least, of chemistry problems. Celsius and Kelvin have the same degree digit interval, which is why converting is just adding 273. We'll use 273.15 in this class. On this conversion, at least for learning the temperature scales, they're just going to say 273. We will want to use 273.15 because it helps for our significant figures later on. Then it won't be the thing causing us to only round to a whole digit number. I'm not expecting you to memorize, again, the Fahrenheit and Celsius conversions because that is a waste of your brain capacity. If we need to do it, we will use the conversion charts built in to the books or the material. Exercise 1. A dog's normal body temperature is given at 102 degrees Fahrenheit, and we want it in Kelvin. So first, we should convert Fahrenheit to Celsius. Again, that would be not something I have you memorize. You could pause it now and look up the calculation if you want, But I'll tell you right now, you subtract 32 and divide by 1.80, and that should give you about 39 degrees Celsius. If we have something in Celsius, all we have to do is add 273 to get our Kelvin temperature, which would be about 312 Kelvin. However, that does not go with what the answer says here, so I'm going to have to do that math again. One moment. All right, I just checked it. The book is wrong. It is 312. Don't listen to that. Here, we'll even change the color. We'll get rid of that. We'll go like this. Haha! I checked my own work that time. What temperature does Celsius equal Fahrenheit? You guys probably remember this because there are two different lines that occur for Celsius and for Fahrenheit. And there is a number right here. If you remember, say it with me. 3, 2, 1. -40. We did it. Because, if they're two different sized scales, then that's just what happens. If we wanted to solve that, though, we would have to check to see when they would be crossing the same x variable. We're going to solve for x. Not really something I cared to work through right now, but if we were to graph it, which would probably make more sense, you could put this equation into some program like Google Sheets or Excel to get -40. But we know that from last year because it was a fun fact. This is how we actually would work to get that. If we knew that -40 would go in here, then we would solve for x. All right, and then we need to talk about density. To determine density, we need to have the mass per volume, or mass divided by volume. Common units in this course are grams per cubic centimeter for solids and grams per milliliter for liquids. Because 1 milliliter equals 1 cubic centimeter, those units are closely related, almost identical. Density is an intensive property, meaning it does not depend on how large the sample is. That makes it very useful for identifying substances and comparing material. Meaning, if I have 1 gram of, let's say, a zinc alloy, and I have 1 ton of that zinc alloy, they will have identical densities because the mass and volume they take up is proportional due to their physical properties. If you were this woman and you jumped in a pool, you might be scared because when you get out of the pool, there's sharp edges all over it. But if you need to measure an irregular solid like this woman, sorry woman, the first record that you would need to take is of the initial, and then when that object that is irregular is in the liquid, then you would measure the difference. This is a super common method when we don't have a simple shape to get its volume calculations from. And it comes up a lot in chemistry, where we need to find the density of an object that is irregular. Alrighty, let's look at this example. A certain mineral has a mass of 17.8 grams and a volume of 2.35 centimeters cubed. What is the density of this mineral? Remember that density is mass over volume, and we are given both a mass, 17.8 grams, and a volume, 2.35 centimeters cubed. If I do that math, I get 7.57 grams per centimeters cubed, and I would have 3 significant figures. So my final density reported would also have those 3 significant figures. Remember that is because we are dividing, and we would go with 3 significant figures. They both have 3 significant figures. There's nothing to figure out there. What is the mass of a 49.6 milliliter sample of a liquid which has a density of 0.85 grams per milliliter? Remember, same formula. We start with the density equaling the mass divided by the volume, and then we should rearrange or reason from our units. So our density is given at 0.85 grams per milliliter. That's our second step. And we are trying to solve for the mass of the sample right here. We don't know what that is. Doing our basic algebra, I would need to get this alone. So mass equals 42 grams. All right, and then this last exercise is going to combine the unit conversions we just did and density. The object has a mass of 243.8 grams and a volume of 0.0125 liters, but the requested density is in grams per cubic centimeter. So we need to convert the liters to milliliters and use 1 milliliter equals 1 cubic centimeter, giving us 125 cubic centimeters. So let's write that down. 125 cubic centimeters. Woof. I'm going to get better at writing with this mouse. Now divide 243.8 grams by our centimeters, because we know that is our density calculation. They gave it to us. It's right there. I'm going to rewrite it anyway, and you're going to have to watch me. There I go. And that would give us, calculator, almost done, 1.95 grams per cubic centimeter. Let's make sure the book agrees. And you'll notice they're asking us in the unit, so we don't have to have a unit down here. Make sure you know how to do that part for a lab or a test so you don't lose points for putting in something that was already understood. But this is a good example of why units should be handled before we put it in a formula, because we needed to know how to get from this to milliliters to centimeters, because those are equivalent, but these are not. If we need to get to centimeters, we need to move 1, 2, right? I think we know how to do this. Let's move on. And here is our last full concept check that is going to combine the displacement and density. Copper has a density of 8.96 grams per cubic centimeter, and 75.0 grams of copper are added to 50 milliliters of water. So we need to first use the density to find copper's volume, and that volume is going to equal the mass divided by density. So if I take the mass, remember mass is in grams, mass, and I'm going to divide that by the density that was given, which is this. That should give us, grams cancel out, that would be 8.37, that was one of my worst ones, cubic centimeters. 8.37 cubic centimeters. That volume displaces about 8.37 milliliters of water, because remember, centimeters are equal to milliliters. If we add that to our 50 mils, because that's how much we had initially, 50.0, and this is 1 decimal point, this is 2 decimal points, so plus 8.37 would give us a final volume recording of, drumroll please, 58.4 milliliters. 58.4. Because we had to round. And wouldn't you know it, that is one of those options. I wasn't even looking over there yet. There we go. So make sure we can connect density after we do our first lab. We'll have to do a little demonstration on density. And we know how to do displacement techniques because we might use them.